Hi and welcome back. This module is on what a Unix-type file system really is. We will have a look at what an inode is. Then we will discuss pointers to data blocks, indirect, double indirect, and triple indirect blocks. We will describe the function and importance of a very special inode, the root inode. And finally, we will have a look at the default numbers of inodes for volumes and how we can manage that. In general, when you ask the question, what is a file system? The answer will usually be that a file system is a collection of files and subdirectories. This is definitely true, but a file system, of course, is much more than that. A nice observation would be that a file system is a tree of blocks. We will definitely explore in a second what that means. So let's start with what a file actually is. A file really is something which is called an inode. This inode has a unique number in the file system, and it contains the properties of a file to start with. In total, the size of an inode in Waffle is 192 bytes, 128 of which are for storing the properties of the file. And with properties you should think of the owner, the size, permissions, and other things. Then there's 64 bytes left for other purposes. We will also discuss that in this module. Now the I in inode, Dennis Ritchie, one of the creators of Unix, wasn't sure what it really meant. He thought it meant index node, but we're just going to call it inode. So to view the properties or the useful properties, you could run the ls-li command. That will also show you the inode number itself. The stat command will give you some additional fields. Now let's first have a look at the ls command, and we see the inode is 561, so there's a list of free inodes in the file system, and whenever you create a new file, then it will pick the first available inode from that list. The type is regular. The dash means this is a regular file. Could also be a directory or a device file, and there are more types. Usually in Waffle environments, the files in volumes are created by NFS clients or CIFS clients, and then that file type will usually be regular or directory. Then we see the permissions. There are 3 sets of permissions, one for the owner, one for the group, and one for the rest of the world. RW- means read write and no execute write. Then after that we have the link count. This is an important one because that means that there is one file name referencing that particular inode 561. If you would create another file referencing the same inode, that would mean that you'd have 2 names to the same inode. That would increase the link count from 1 to 2. We'll have a little demo on that in a second. Then we see the owner of the file, and we also see the group. So it's owner and group both in the inode. Then of course the size, as you can see here, is 0 bytes. So this is an empty file. And then we have the date. There's one date that is shown with the ls command, which is the date of last change. So when was this file last modified? And finally we see the file name. As I said before, the file name is not in the inode. This is the only entry that you see here which is not part of the inode itself. It is in a directory data block. So there's a file name that references an inode. And if you'd have more file names, your link count would increase. So let's do a quick demo on that. I've logged into a Linux machine and I'm going to create some files. I create a new directory and change to that directory. Then when I look inside, it says there are no files in here. Now I'm going to create a file which is empty and it's called file1. Now when I run the ls-li, it tells me this is the inode and this is the link count. So there's one file name referencing that particular inode. Now if I create a hard link and run the same ls again, it says now you've got 2 file names referencing that particular inode, and so the link count is 2. I have 2 links to that inode. I can create a third file and run the ls command again, and now it will tell me that I have 3 links to that particular inode. So file 1, 2, and 3 are all the same file. It's just the name that differs. Now I put some data in file 2 or file 3, it doesn't matter. I will see that all of a sudden the size of the file is 5 bytes, no longer empty. And I can change the permissions to read, write, execute for the owner. then they all seem to have changed because it's only one file with one set of properties. And of course, if I remove a file, my link count will be reduced from 3 to 2 because I've removed a file name, and so on. So I can remove any of the 2 files that are left, and I see that the link count is reduced to 1. And then if I finally remove the last file name, that will mean that the inode will be freed and stored in the free list of inodes and can be used again for a new file. So that's a hard link. And we're done. The stat command will give you some more information. We see 3 dates, for example. The first one is the one that the file was last accessed for reading, and the second one is when the contents of the file was last changed. That's the date you see with ls as well. And the third one, that's the date the inode itself was last changed. And these 2 numbers reference the device on which the file resides. So in our case, that's a flexible volume. It's not a big issue, but if you want to avoid writes when you only intend to read, then you should change the access time update to false per volume. Up till now, we've only talked about inodes, but what about the data of a file? The data of a file can be stored in the inode itself, or in a data block that is referenced from the inode. How does that work? If a file is 64 bytes or less, then the data will be stored in the inode. If it's more than 64 bytes, then the inode will get pointers to data blocks. Each pointer uses 4 bytes, so in the 64 bytes that's left in the inode, you can create 16 pointers. And each pointer references a 4K block, so that's 64 kilobytes. So if a file is larger than 64 bytes, but not larger than 64 kilobytes, then there will be 16 pointers to direct data blocks. If a file is larger than 64 kilobytes, then the pointers from the inode will point to indirect blocks. So these blocks do not contain data, but they contain pointers. And since a pointer takes 4 bytes, you can have 1024 pointers in a single 4K block. So from the inode, you have 16 pointers to 4K blocks that all have 1024 pointers. That gives you a total of 64 megabytes. And if the file is larger than 64 meg, then double indirect pointers are used. That will allow for 64 gigabytes. And there are also triple indirect blocks that will give you 64 terabytes. Now the last thing I heard was that the maximum file size in ONTAP is 16 terabytes. So triple indirect blocks should be more than enough. Now all of these blocks and inodes should be accessible in a structured manner. This is where the root inode comes in. At the top of the tree of blocks there is a starting point which is called the root inode. This inode is in a fixed position and always has number 64. So if you have, for example, 5 volumes, you will have 5 root inodes and they all have number 64. In short, the root inode offers a path to the files in the volume. This root inode is usually mounted to a junction path in the root volume of the storage virtual machine. Now there's one last thing that I would like to discuss on inodes and data blocks. How many inodes can a volume have? When you create a volume, one inode for every 36 kilobyte of space in the file system is reserved. So for example, a 20 megabyte sized volume will get 566 inodes, one for every 36 kilobytes. To list the number of available inodes, you can run df-I from the cluster shell. Or you can run vol show and then list files. And if you want to change that number, so if you want to increase the number of inodes, you can run the vol modify command. The maximum number of inodes in a single volume is 1 for each 4K block. Now I hope all these numbers and blocks didn't scare you off, but maybe we should finish this with simply stating that a file system can be regarded as a tree of blocks. So I could have just said a file system is a tree of blocks. Now let's go and have a somewhat longer demo on this topic.